Okay, thank you. So this is joint work with Nikhil Srivastava, who was at Microsoft Research in India and is moving to Berkeley as of January, and Adam Marcus, who I should mention has a stranger position. So he's mainly at Crisply, which is a startup company, where he works half-time, and then half of his time they just let him do math, and he works with me. But he will probably take a job at a university next year, I believe. Okay, so the Kadison-Singer problem is an old problem, and that naturally comes in operator theory. And I will tell you a little bit about it, but I need into the next slide, but I will be honest with you. I understand it formally, in the same way as one would understand a dog from looking up the definition in the dictionary. It's different from having a dog. So we will discuss the original problem briefly, and then I will explain to you the animals that I really understand. So it was known to be equivalent to many other problems. Some of these really are the animals that I understand. And the first ones I will explain to you at least Anderson's paving conjectures and the Ackermann-Anderson paving conjectures. And then I will go to proving Weaver's KS2 conjecture, which is known to imply it. And then at the very end of the talk, I will mention that you can use the same techniques to prove Anderson's paving conjectures, which I'll explain. So I'll give you some of the story here. So first, the Kadison-Singer problem. So it's about bounded operators on L2. And you start out with looking at a maximal abelian subalgebra of this. So think about infinite dimensional diagonal matrices. And then you take a look at states, which are linear functionals on these, which are positive. So if you throw in a positive semi-definite operator, or I'll think of it, you'll get a positive number back. On the identity, they should be 1. Pure states are the ones that cannot be expressed as a convex combination of any others. And any pure state from the maximal abelian subalgebra has a very natural extension to a state on the entire algebra. Essentially, ignore the non-diagonal elements that you're dealing with. But the question of Kadison-Singer was whether or not this extension is unique. Okay, we will not think so much about this version of the problem, but I know that for many people this is a very natural thing to think about. If you wanted to understand it better, the two things I recommend reading about it are either Nick Harvey's survey on it or Terry Tao did a nice blog post about it. Okay, so here's one of the animals I do understand, Anderson's paving conjecture, which is really about finite dimensional matrices. So in this problem, you're given a matrix, and you want to partition its rows and columns. It should be a symmetric matrix with 0 diagonals. So we want a symmetric partition of its rows and columns. Think of it giving, when I partition the rows and columns, I get some subblocks. After rearranging them, they can look like this. They're not necessarily contiguous. And what you want is that the norm in each subblock should be much smaller than the norm of the original matrix. Okay, this is where having a condition on the trace is very important, or the diagonals being 0. For example, if your matrix were the identity, there'd be no way. The norm would be 1, and for every subblock, it would be 1. But if you have 0 diagonals, then this becomes reasonable. And then the quantification is for every amount smaller that you want the norm to be, or every epsilon greater than 0, is there a number of blocks into which you can partition the coordinates that's just a function of epsilon and independent of the dimension, so that you can achieve this. Okay, we will play with this again later, and I will explain problems like this in much more detail soon. But I guess I should mention that once you know this statement in the finite dimensional case, then infinite dimensional variant follows. So that is, instead, you have a bounded linear operator on L2, and now you need to basically partition the coordinates, but now it's the natural numbers into a finite number of subsets. And this follows pretty immediately. On the other hand, I know how to give a proof that is very natural in the finite dimensional case. I have no idea how to extend that proof to the infinite dimensional case other than by taking a limit. So, on the other hand, right, I want to go to be more concrete. So Anderson's paving conjecture like this was proved by different people to be equivalent, or you could assume more and more facts about your matrix. You could assume it suffices to prove it for some fairly nice families of matrices, and what's important to me is this result that says it suffices to prove it for projection matrices, which are really like the simplest matrices I can think of. as you do this reduction, it changes the relationship between k and epsilon. But still, if we just want for all epsilon there is a k, you can deal with projection matrices. And the version of this I will eventually tell you how to prove was described by Harvey, which is just now a statement about vectors that you get from this projection matrix. So imagine I have n vectors in d-dimensional space, so that they are a decomposition of the identity. There's some of their outer products of the identity. And I need an upper bound on their norm. The norm squared of all of them should be less than or equal to a half. This a half turns out to be very important. The conjecture is that I can then partition my vectors into k different sets, so that the norm of the sum of the outer products in each set is at most 1 minus epsilon. And this is equivalent to Anderson's paving conjecture. And you will see by the end of the talk how you would prove something like this. The 0 on the diagonal disappeared when they turned it into a projection matrix. Right. There's no restriction with the projection matrices. OK. So this is sort of an overview of some context. I'm now going to essentially begin my talk again. I want to be very concrete and try to get you some understanding, or give you some understanding of what's going on in the way I think about this problem. OK, so let's just think about decompositions of the identity in moments of vectors. So to be concrete, let's put our vectors in RD. There's really everything we thought about was in RD, and all the proofs just work for the complexes. So we can. OK, so if I give you a bunch of vectors, v1 through vn, I want to talk about what is their moment in a given direction, which for me is a direction I specify by a unit vector. And take a look at the sums of the squares of the inner products of the vectors with you in that direction. So for example, if I have just two vectors, v1 of length 1 and v2 of length 2 here, the moment in this direction is 1. In this direction, it's 4 because we're taking a sum of squares. And halfway in between, it's 2.5. Now, the moments of vectors we can express by a quadratic form. So the moment in direction u, the sum of squares, I can take by writing each square, flipping it around, rearranging terms. It's just the sum of the outer products of the vi's, and that gives me the quadratic form. So for any direction u, I can find the moments from this. And what we're going to be interested in is sets of vectors with spherical moments, or what we often call vectors in isotropic position. OK. I am going to draw, that's when the moment in every single direction is 1. And I'm going to draw these, or I think about these, as having both a vector and its opposite. You don't need to. It doesn't matter, because having the vector and negative of the vector makes no difference in this formula. But I try to think of this as like a very balanced object. I imagine that I have a bunch of rods that all are welded together at the middle, sort of like jacks that you play with as a kid, but generalized in high dimensions in many of them. So this is equivalent to the sum of the outer products being the identity. And the question we're interested in is whether or not when you have one of these, which is spherical, can I partition the vectors into two sets so that now in each set it's approximately half spherical? And half spherical, it should mean that all the moments in every direction are near a half. And we'll put precise numbers on that. But yeah, so if all the moments in every direction here were 1, you'd partition it in two parts. The sum of the moments in any direction will always be 1. But I want to make sure that in every direction both of them are near a half. So how near a half? Well, you could think about 3/4 or something like that for now. So a reasonable condition would be that I partition them into two sets, and the moments in every direction is between 1/4 and 3/4. That's something we'll want to do. OK, let me begin by simplifying how we describe this. It's equivalent to say that then for each set, the sum of the outer products of the vectors in each set as a matrix, its eigenvalues are between 1/4 and 3/4. And that actually, I only need to look at one side. Because I'm now going to consider partitions into two sets, I only need to say that the eigenvalues for each set are at most 3/4, because the eigenvalues for the other side are 1 minus whatever they were. So I can just look at one set. Or in particular, I will talk about the norm of the sum of the outer products, which is just the largest eigenvalue, because we have a Hermitian matrix. And it's positive semi-definite. OK, so the question is, when can we do this? And there is an obvious obstacle, which is large vectors. If I have some vectors of large norm, there's no way to partition them into two sets to be half spherical. For example, if one of these just gets one large vector and the other gets them like this, then you get these very distorted ellipses. Or if I put both of the big vectors in one set and the two small vectors in the other, I get spherical moments, but they're not near a half. Okay, what we're going to prove is a variant of Weaver's conjecture, which says that this should be the only obstacle to being able to partition them into half-spherical sets. So Weaver's conjecture is that if all of the vectors are small, so there's some constant, everything has to be dimension-free, some constant alpha, so that if all the vectors have squared norm at most alpha, then I can partition the vectors into two sets, so that all the eigenvalues in both sets are at least bounded away from 1 minus epsilon. It's actually not a very ambitious conjecture.
You wanted more.
I wanted more to be a half, but actually this suffices to prove Kadison-Singer. So this is all you need. Yes, so we are going to prove more. What we will prove is actually you can get as close to a half as you like. So if I bound the norms of the vectors squares by alpha, then I can partition them in two sets where I get as close to a half as I want. It's the most 3 plus root alpha. The constant is actually a little better than 3, but it's easier to write 3 on the slides. So no, the bound I'm going to prove for you is not tight. It can be, oh, sorry, it's tight up to the constant. I will make a conjecture about what the tight case is at the very end. I think our proof, this alpha needs to be less than a fourth, and you should be able to do it for anything less than a half. And
But the dependence on alpha.
yeah, the dependence on alpha is tight up to a constant, yes. You could check that by taking like random sets of vectors or something. OK. Yes, please. I'm sorry, say it again. Oh. Yes, before taking small. OK, so before, when I had, OK, so in order to get a partition into two sets, I need the norms to be relatively small. If I'm going to allow the norms of the vectors to be as large as a half, then I need a partition into many sets. If you actually made the vectors have norm a half, you can't do this with a partition into two sets. My lecture will be much easier if I just talk about two sets for now until the end. And later at the end, I'll bring up many sets, how we deal with that. I think that'd actually be obvious, but yes. Yeah, you could do that too. You can do something better. OK, so my first instinct when looking at this problem is to say, well, what happens if I choose a random partition of my vectors? I mean, I was raised in probabilistic combinatorics, so I say, what if I just choose them into a partition of the random set? And this sort of almost works, though you do get a dependence on the dimension. So you can look at variants of the matrix Chernoff bounds or Rudelson's concentration theorems. The one we need is one by Joel Tropp. It tells you that if all of the squared norms were at most 1 over log the dimension, then a random partition would work. So these are theorems, for those who aren't familiar. They're basically concentration results. And sort of standard concentration results say if I add a bunch of numbers that are all small, then you can say that they'll be tightly concentrated around the expectation, the sum. This sort of says the same thing for matrices. And the matrices being small corresponds to the norms of the vectors. OK, but random partitions in general will not work. And here is a very simple case that breaks random partitions. What if my vectors, all of the same norm, the norm squared will be alpha, and they're all just copies of elementary unit vectors? So this is projected from 3D down. So I take elementary unit vectors. And you can take a look at it. Just take each one repeated. How many times will I have them? I'll have each one 1 over alpha times, if alpha squared is the norms of the vectors. In this case, a random partition will fail. And the reason is, so imagine I make a random partition. I color half of them red, half of them blue at random. Or at least a random partition usually fails. And the reason is because in any particular direction, they're 1 over alpha vectors. So there is some chance that they all get the same color. It's not big. It's 2 to the minus 1 over alpha, or twice that. But I'm keeping alpha fixed as the dimensions grow. And there are a lot of dimensions. So if you take a random partition, it tends to fail. On the other hand, you know how to solve this problem with the elementary unit vectors. You take half of them in each direction, and you just partition like that. OK, so for me, the next sanity check actually came from expanders. So let me give you a construction that's just a little more complicated than the elementary unit vectors. What we do is we take a graph, and I will use it to make a collection of vectors. If my graph has n vertices, I will make, and m edges, I will make one vector for every edge. They'll live in Rn. And what is my vector? So AB is an edge, meaning the vertices are A and B. It's a vector that's all zeros, except it's got a 1 for one of the vertices and a -1 for the other. So this vector lives in Rn. And if I take a look at the sum of their outer products, I get the Laplacian matrix of a graph. Now, if my graph happens to be an expander, then this is not exactly a spherical set, but it's very close. If my graph is a good expander, all of the eigenvalues are close to D. So I could divide by D and get something that's very close to vectors in isotropic position. And I'm very happy to say that in this case, we know that you can partition the set of edges into two sets that are both expanders. So these are theorems of Broder, Friese, and Upfall, and Friese and Malloy, who show that if I have an expander, I can partition the edges and I get two different expanders. And the way they do the analysis is they use a random partition. It usually doesn't work. But they use a tool called the Lovász local lemma, which at least proves that there is a non-zero probability that it works, and that a random partition is good. So at least we knew before getting into this that for this one other interesting case of expanders, we could basically, Kadison-Singer is basically true by the Lovász local lemma. On the other hand, we spent a long time trying to generalize this, it seemed to depend very heavily on the fact that the vectors are sparse. OK, so you could extend this, these vectors I gave you from the graph only had 2 non-zero entries. You could extend it up to a constant number of non-zero entries and still make the argument work. But eventually it breaks down. OK, so now let me tell you how we're going to prove it. First, I'm going to make my life easier. I wanted to say that I want all of the eigenvalues of this matrix to be at most a half plus 3 root alpha. And for this matrix, let me put the two matrices together into one big matrix. So here we'll put a block of zeros, and here we put another block of zeros. And of course, the eigenvalues of the big matrix is the union of the eigenvalues of the individual ones. So I just want the eigenvalues of this big matrix to be at most a half plus 3 root alpha. OK, instead of looking at eigenvalues directly, what we're going to do is we're going to just recall that the eigenvalues are the roots of the characteristic polynomial. So we're going to look at the roots of the characteristic polynomial of this matrix. And then we're going to do something a little strange. We're going to consider the expected characteristic polynomial when I choose a random partition of the vectors. So as opposed to looking at something like expected eigenvalues, we will take a random partition of the vectors in two sets S1 and S2, and we will look at the expected characteristic polynomial. And the way we will prove that there exists a partition into two sets that achieve this is by analyzing these expected characteristic polynomials. And I will prove to you 3 facts about the polynomials. One, that this expected characteristic polynomial actually has all real roots, which I should remind you is not obvious, because you're taking the average of polynomials that have real roots. There's no particular reason that should have real roots. 2, we'll prove that its largest root is at most this bound that I want, the 1/2 plus 3 root alpha. And then we are going to prove that that is actually meaningful. Actually, I'll do it in the other order. We will prove that the polynomials that we are averaging correspond to something that we call an interlacing family, which I'll define for you in a bit. And that means that there is always one whose largest root is at most the largest root of the average. So once I know that they're what I call an interlacing family, I will know that there happens to be one whose root is at most this, and that's the bound that I need. OK, so let's take a look at this expected characteristic polynomial. I need to introduce some notation, give it a name. So first, I want to come up with a good way of describing my partitions. So I will do it by a bunch of indices, sigma 1 through sigma n, where sigma I is 1 if vector I is in set 1, and it's 2 if vector I is in set 2. So in particular, I can describe a polynomial as just a p sub sigma, where these are all numbers 1 or 2. And those tell me which set each vector goes in. Yes? I'm sorry, what? Oh, yeah, this polynomial, yeah, eventually we'll write it as, that's the characteristic polynomial. Right, so eventually we'll write it as a determinant of, but yeah, I'll keep talking about it for now as a characteristic polynomial in some variable x that we'll never actually use, or maybe we'll use it. We'll see.
When you say
Yes.
expected, we take all possible subsets.
Yes. So in particular, what we're going to do, I'll make it on the side. We're going to choose the sigmas at random, each 1 or 2 with probability 1/2. So we'll do the uniform distribution. And to make my life a little easier, let me, instead of talking about partitions, talk about random vectors. So what we'll do is, if I put vector I in the top part, or in the first set, I will make a vector AI, which is vi up top and a block of zeros down bottom. In the other case, when I want to put it in the bottom, I make a vector AI, which is 0 in the top block and vi down bottom. And if I do that, I can now look at the outer product of all of the sum of the outer product of the AIs, and it is this same matrix, but a lot more compact to talk about. And now really what I'm doing is I'm really talking about having, as opposed to a random partition, I can talk about each AI being a random vector, which is equal to this vector with probability 1/2 and that vector with probability 1/2. OK, so in general, we're going to look at the expected characteristic polynomials of the outer products of random vectors. We call these mixed characteristic polynomials for a reason that may eventually become apparent. So if you give me any set of vectors, a1 through an, as long as they're independent, we will take a look at the expected characteristic polynomial of the sum of their outer products. And one of the first things I will tell you, and it's easy to verify, is that the expected characteristic polynomial does not depend on the distributions of the AIs in particular. It just depends on their covariance matrices. So for each random vector, it only depends on the covariance, literally the expectation of AI transpose. I'm sorry, I'll usually say transpose instead of star. But so this polynomial will only depend on those. And the polynomial is real-rooted. And I will tell you how we prove that it's real-rooted. But first, let me tell you, because it only depends on the covariances, I don't really think about it as a polynomial related to the distributions anymore. I just think about it as a polynomial in the covariance matrices. So I will denote this by mu of a1 through an. And right, because this is just a polynomial in the covariances. There are 2 things I just want to remind you of. What do we know about these covariance matrices that I'm going to use a lot? So I'll tell you before we go on. First, the trace of one of these matrices, just by using elementary facts of the trace, is the expected norm of AI squared. And so we know the traces are at most alpha. So all the matrices have a small trace. And the sum of these matrices is now a 1/2 times the identity. Why is that? Because you had an identity. The sum of the vi stars was the identity. But now you have that in the upper block, that in the lower block, but with probability 1/2 of each. So you get a 1/2 times the identity. OK, that's it. I usually like talking about vectors and isotropic position and things like that. So in the next few slides, I'm going to hide a factor of 2 and talk about matrices where the sum is the identity again. So if something looks off by a factor of 2, don't worry. It'll make our theorems cleaner. OK, so these mixed characteristic polynomials we know a lot about. One reason we named them this is that the constant term of these polynomials is called the mixed discriminant of a collection of matrices. And there's a lot that we know about these. And it was actually this is where our proof came from. So why don't I tell you a few places, or the origin of our proof. So actually, more than the mixed discriminant, if I just have diagonal matrices, so and I need a number of matrices equal to the dimension. So if D is equal to n, I take a bunch of diagonal matrices, and I look at this mixed discriminant, our constant term, it actually is equal to the permanent of the matrix that I get by taking each of these diagonals and putting it in a column of this matrix. So it's a matrix permanent. And one of the famous things we know about matrix permanence, which is if I assume the matrix is doubly stochastic, meaning row sums 1 and column sum 1. That's the same thing here as assuming that the sum of the AIs is the identity and the traces are all 1. Van der Waerden's conjecture was that the permanent is minimized when I take the matrix all of 1 over n, which is in this case when all of my matrices were the same and 1 over n times the identity. So this was first proved by Ogoryev and Falkman. We're not going to look at their proof. We're going to be motivated by a very beautiful proof of this fact by Gurvitz. That this is a lot of combinatorics. Gurvitz's proof will be the sort of algebra I talk about. By the way, much easier than reading Gurvitz's paper if you want to look at it. There's a paper by Laurent and Shriver that is much cleaner to read. OK, so Gurvitz actually proved more than bounds on the permanent. He proved a lower bound on the mixed discriminant. It was a conjecture of Boppet that actually, when I had a family of matrices like this, where the sum, Hermitian matrices, where the sum is the identity and all the traces are 1, the mixed discriminant would be minimized if all the matrices were just multiples of the identity. And Gurvitz proved that using the same technique. So this was very useful to us, because this actually gives us a lower bound on the constant term of our polynomial. And I should mention, you can use Gurvitz's technique to get lower bounds on all the coefficients of the mixed characteristic polynomial. Unfortunately, getting lower bounds on the coefficients of a polynomial doesn't tell you much about its roots. But the mathematics he introduced was very useful. So the way he got at this is through the theory of real stable polynomials. So some of you will be very familiar with these, but for those who are not, I should say it's a multivariate generalization of what it means for a univariate polynomial to be real rooted. So one way of thinking about, you can define real rootedness in many ways for a univariate polynomial with real coefficients, but one way of thinking about it is to remember that if there are complex roots, they come in conjugate pairs, one above the real line and one below. So if I have a polynomial with real roots, I could say it's real rooted if there are no roots above the real line with positive imaginary part. OK, that is a definition we can generalize. So you say that a multivariate polynomial is real stable if whenever all of the variables are above the real line, it doesn't have a root. So I describe this as having no roots in the upper half plane, but it's really, think of maybe as it's like a quadrant or something. If all of the variables have positive complex part, then there will be no roots. By the way, this is also sort of isomorphic to Garding's theory of hyperbolic polynomials. And this is the theory that Gurvitz used in his proof that we're going to exploit as well to bound the roots of the polynomials. So I need to tell you 2 or 3 things about real stable polynomials. Actually, there are a lot of interesting things to know about them. If you want to read more, there's a survey of surveys of Pimentel and Wagner are very nice for learning about these. OK, so first, let me tell you a real stable polynomial. By the way, the first place I saw this in print was Brandon and Borsea. I'm sure that someone knew this before. And it says if I take positive semi-definite matrices A1 through AN, and I take the determinant of the sum of these matrices with variables in front, that polynomial in the variable Z1 through Zn is real stable. And this is very easy to prove. I won't prove it. If you want to think about it, I'll give you one hint. First, prove it for the positive definite case, and use the fact that positive definite matrices have square roots. And once you know that, it's relatively simple. We need 2 other facts about real stable polynomials. I have a way to build them. We also need operations on real stable polynomials that preserve real stability. We're only going to need 2. One, from the work of Lieb and Sokol, well, rotated 90 degrees, but it's the same theorem, is that if you subtract off the derivative of the polynomial in any one of the variables, it is still real stable. So if I take a polynomial, say subtract off the partial derivative in zi, I get another real stable polynomial. This, you might be familiar with the one-dimensional analog of this. If I take a polynomial that's real rooted and I subtract a multiple of its derivative, you still get a real rooted polynomial. And actually, you'll see why that is in a little bit, too. The other fact I need is if I have a real stable polynomial, and I just set all of the variables to be the same to make it a univariate polynomial. So substitute x for all of the zi's. That is now a real rooted polynomial. And that's, again, just trivial, because if you had a complex root, it would lift to another one here. OK. So now I can tell you everything you need to know why the mixed characteristic polynomial is real rooted. It's because it is equal to this. OK, so the mixed characteristic polynomial I form by taking the determinant of this. I make a polynomial in many variables, z1 through zn. I take the determinant of the sum of the zi's times the ai's, where those ai's were the matrices in my mixed characteristic polynomial. I now apply the following operator. I subtract off the derivative in the first variable, then I subtract off the derivative in the second, and I apply that to all the variables. And then I set all the variables to be the same. And that is equal to the mixed characteristic polynomial. So I'm not going to prove that for you, but it's an equality. So once you know an equality like this, you can prove it. Or as I'm always telling my graduate students, proving equalities is easy. It's inequalities that are hard. And we wrote an initial proof of it in our first draft of our paper, and actually a couple of people sent us simpler proofs thereafter. So that is the other problem. Once you know that it's true, you can also write an ugly proof of it. But it takes some work to make the simple proof. But OK, this is all you need to know that every mixed characteristic polynomial is real-rooted. We start with a real stable polynomial. We apply operations that preserve real stability, and therefore we get a real-rooted polynomial. OK, now before I bound the roots, I'm going to tell you about interlacing families because it's very simple now. And this is how we're going to be able to argue that one of the polynomials in our ensemble has the root bound we desire. So first, what does it mean for two polynomials to interlace? It means their roots do this, essentially. Again, think of a polynomial and its derivatives. Between every pair of roots of one, there should be a root of another. We're going to be interested not as much in interlacing as when two polynomials have a common interlacing. So two polynomials have a common interlacing. I think of my polynomials as these blue curves here. If there is another polynomial that interlaces both of them. So think of its roots are these betas I've drawn here. So that means I have two roots. Each polynomial has a root, and then the interlacer does. And then they have another root, and then the interlacer does, and so on. Another way of saying this, which is a little easier, often is it says if I take a look at the roots of the interlacer, it gives me a partition of the real line into intervals, in each disjoint intervals. And each of those intervals contains one root of each polynomial. That's what we really need. So we're going to be interested in having common interlacings, and this is how I'm eventually going to define for you an interlacing family. But first, let me tell you the key point about common interlacing, which is a trivial fact but is incredibly useful. If two polynomials have a common interlacing, then at least for one of them, its maximum root is less than the maximum root of the average. And let's just prove that. Take a look at these two polynomials. They have a common interlacing. So let's look at the largest root of the average. That'll be somewhere here. One of them they should be monic. They should both be going to infinity as the input goes large. So they both go off to infinity. One of them is positive here. One of them is negative here. OK, but you know that we're looking after the largest root of the interlacer. So you know they were both negative here. You know they're both eventually going positive here. So one of them, and they can only have one root here. So one of them has to go to get a root here, which is lower than that. So just by drawing pictures, you can see that if two polynomials have a common interlacing, then the largest root of one of them is less than the largest root of the average. Actually, if you play with this fact enough, you get so used to it, you forget that it's not always true. Just as I often forget that not all matrices are diagonalizable. So let me just give you a few examples otherwise. So if I take two polynomials like this, here are two simple real-rooted polynomials. I should remind you their average has no real roots. And worse can happen. I can take two real-rooted polynomials like here. You might not be able to see. This one does touch down twice here at 9 and 10.3 approximately. I can take two real-rooted polynomials whose average has real roots, but for which my condition still doesn't hold. So it's not just about the average being real-rooted. These two polynomials, their average, this red curve here, does have real roots, but its largest root is less than the largest root of both of these polynomials. And the reason that can happen is in this interval, the green polynomial had two real roots, and the blue polynomial didn't have any. OK, so this is just to remind you, this is not always true. OK, but for common interlacing, this will work. Now, some of you might be wondering, why am I using this interlacing property that talks about all of the roots, when clearly all I'm exploiting is the largest root? And the answer basically is I know how to tell when two polynomials have a common interlacing, and I don't know how to reason just about their largest roots. OK, so there's a very easy condition for two polynomials to have common interlacing. It's that every convex combination of them should be real-rooted. So if I have two polynomials where every non-negative sum of them is real-rooted, that's if and only if they have a common interlacing. Okay, and this is something I can reason about. even though in theory we could get away with less for this argument. We'll return to that, because of course this is how I'm going to prove to you that the polynomials have some nice interlacing properties. But I now need to tell you what an interlacing family is. Okay, we say a set of polynomials is interlacing. If I can draw a tree, or is an interlacing family, where each polynomial in the family appears at a leaf of the tree. And at intermediate nodes, I take the average of the polynomials beneath them. So in my case, my polynomials have a very nice structure. I describe them by these coefficients, sigma 1 through sigma n. And so this polynomial here, let's say I could fix all the first coefficients and let the last vary. So this could be the average of polynomials p11 and p12. So far, this could be the polynomial of p2i. This could be the polynomial, the average of them all. Okay, I put them in this tree, and I need the fact that every pair of siblings has a common interlacing. So these two have a common interlacing, these two have a common interlacing, and so on. Okay, this is what I really need from my polynomials. Now, to simplify notation, instead of get rid of these expectations and all, let me just call this polynomial here p1, meaning it is all the first coordinates were 1. And this polynomial I'll call p empty string, or empty set, because it's at the top. I'm averaging over everything. Okay, so the main fact we need about these interlacing families is that when you have a family of polynomials like this, there is always a leaf whose largest root, that's a poor word now, whose largest zero is less than the largest zero of the polynomial at the root of the tree. So if I know the largest root of the average of the polynomials, there will be one whose largest zero is less than that. And the argument is trivial. This polynomial is the average of those two polynomials. So one of them has a largest zero less than the largest zero of this. And then you just walk down the tree, because our condition is that every pair of siblings needs to have a common interlacing. That's exactly what you need to walk down the tree.
So you're really producing a very rare event.
Yes. Oh, yeah. It could be a very rare event. And there are cases where it is. I mean, if you think about the examples of when I start out with all unit vectors, or elementary unit vectors, and I take a random partition, it's almost always bad. And that's the hard thing, right? Trying to say when you have events that are almost always bad, trying to prove that they're at least sometimes good that's sort of the hard case. This could be very rare. Okay, so now I want to prove to you that our polynomials are an interlacing family, and it will be easy now. So again, just recall how I parameterize them. Oh, yes, sure, please.
In the end, you just wanted the biggest. But
Yes.
You're arguing that you have to look at all of them.
Yes.
And the reason is that you,
Yeah.
it's a tree argument.
Right.
Just simply because
It's the only.
It's too little information.
Yeah, just looking at the largest root, I just don't know how to reason about the largest roots in these families directly. So I do it by common interlacings and proving that things are real rooted. So yeah, it's just the only way I know how to go about it. I mean, there are other arguments we have using this technique where we are interested in roots in the middle somewhere, but then that's a different business. But not for this paper. Okay, so if I think about it. Yeah, the next talk will be the largest one. A year and a half from now, you may hear talks with the middle. Okay. So remember, we specify our polynomials. I tell you where the first vector goes, where the second vector goes, where up to the nth vector goes. And my interlacing family will say, OK, fix where the first k vectors go. So fix sigma 1 sigma 8, randomize, take the expectation over the others. That will be my node in the tree at the corresponding sigma, at height n minus k. Height k, I guess. Yeah, n minus k. So what I'm going to do is I'm going to consider populating this tree with this. All the polynomials of everything are fixed at the bottom. The top is the average. And intermediate, I fixed where some of the vectors go. And I need to prove then that siblings at those levels have a common interlacing, which means I need to prove their average is real rooted. OK, and here was the theorem I told you. How to prove that they are real rooted is I need to show that the convex combinations are real rooted. Sorry, to prove they have a common interlacing. So what I'm doing is I'm taking two polynomials where I've fixed sigma 1 through sigma k. And now I'm just varying the next coordinate. I'm either setting it to 1 or 2. and I'm taking an average of these. So this one times 1 minus lambda, that one times lambda for lambda in 0, 1. And the other coordinates are random. Okay, this is just another mixed characteristic polynomial. It's the mixed characteristic polynomial, because again, mixed characteristic polynomials, I just need a probability distribution on all the vectors. Okay, for sigma 1 through sigma k, it's the trivial probability distribution. Those things are just fixed. Sigma k plus 1, where the k plus vector goes, I choose it to be set 1 with probability lambda, set 2 with probability 1 minus lambda. That's really what's going on here when I'm taking the convex combination of these two polynomials. I'm taking, because it's the sum of them. And the others are just uniform, 1 and 2 with probability 1/2. So the bottom line is the average of my siblings is another mixed characteristic polynomial. And that is how I know now that it is real rooted, and therefore all siblings in my tree have common interlacings. Boy, I might be going even a little too fast, so ask more questions. I count on people to slow me down. Yes? If some roots are repeated, you can still have interlacings. You just need to, look at them the right way, which is, if you have you can have 3 roots on top of each other and 2 in between or something like that. And you just take the right yeah, it doesn't hurt anything. Mm-hmm.
Given this, what would happen if initially, instead of picking each vector to be in one of the 2 sets with probability 1/2 and 1/2, you do it with probability 1/3 and 2/3?
Yeah, whatever probabilities you want, the same thing holds, yes.
Because you are really looking at, where you get 1 part.
Yes. Yeah, and you can do fancier things if you want. Yes.
I'm unclear how you use the root. So it's some kind of a relaxation of the partition?
You mean looking at this average or looking at?
Yeah, so something of it as an algorithm.
Right.
It's not an algorithm.
Right. Well, it is. It's just an exponential time algorithm.
Yeah. So
right.
Can you say that viewpoint for the?
Yeah, at the end, maybe I'll ask a question. We don't know how to do this faster.
I know.
Yeah.
But translate it to what?
Oh.
So the translation.
Oh, the translation. Okay, if I wanted to think of it as an algorithm, what I would do is, okay, I guess I'd go back to this tree. And it looks a little bit like a martingale type argument, where if I know the largest 0 of this polynomial satisfies the bound that I want, and then I need to go down the tree, and I know one of them will have the correct largest 0. In case people are wondering why this is an exponential time algorithm, evaluating these polynomials high up the tree is hard. As I told you, even getting the constant term is like computing a permanent, and that is essentially an exponential time thing. So we can't evaluate the polynomials quickly, but there is always one that is good, and you can just walk down the tree to find the particular one you want. So it's like the method of conditional expectations or something, if you try to think of it algorithmically. Okay, so now I'll tell you how we prove an upper bound on the roots. And here's where I'm hiding the factor of 2 to make things pretty. I have a family of matrices, let's say, so that the sum is the identity, and all the traces are bounded, let's say less than or equal to epsilon. We will then prove that the maximum root of the corresponding mixed characteristic polynomial is at most the square of 1 plus root epsilon. And the AIs are Hermitian. And oh wait, positive semi-definite too. Yes. And yeah, then we know the sum of the AIs is the identity. Right, we don't need that they come from this distribution on 2 vectors. And in particular, the tight case doesn't come from that. So this bound is asymptotically tight, meaning you couldn't prove a constant lower than this. And the tight case is, okay, sorry, when I say it's asymptotic, yeah. The tight case is when all of the matrices are just a multiple of the identity to get the trace to be epsilon. So you need, if you make them all multiples of the identity, this will come. Then what this actually turns out to be is an associated Laguerre polynomial. And it's the natural thing you'd get from random matrix theory, and this is the right bound on the roots. Yes?
Would you remind me what the new polynomial was?
So I gave you okay, so it was the expected characteristic polynomial when you sample vectors whose covariance matrices are the AIs. So you take the outer products of vectors whose covariance are the AIs, and you look at the expected characteristic polynomial. But I will also give you a definition. Yes, that, yeah, you take the, right. But you should think of it as not the expected matrix, but the expected characteristic polynomial of the matrix, which is different in a very critical way. OK, so I should tell you, because of the factors of 2, and in our special case, getting an upper bound here of 2 would be trivial. An upper bound of 2 is easy. Any constant strictly less than 2 would prove Kadison-Singer. And we'll get it as close to 1 as you want just by changing the condition on your traces. OK, how are we going to prove this? The same way we proved the polynomial was real-rooted. The same formula. We recall this formula for the mixed characteristic polynomial. I have a determinant. I subtract off derivatives. And then I set all the variables to be the same. Actually, I should tell you that initially, there are unfortunately many ways to prove that polynomials are real-rooted. So when we started working on this a few years back, we had a different way of deriving the mixed characteristic polynomial and proving it was real-rooted. So, similar operations, but different. And I think that delayed us for many years because that formulation did not lead to a natural bound on the roots. This one does. Once we saw this, then the whole theorem fell in 2 weeks. So we had a different proof of real-rootedness before. This one, we needed some work. So I'll tell you now how we're going to prove an upper bound on this. It's going to be a sort of algorithmic procedure where I'm going to, if I just had the determinant here, I cannot tell you everything you want to know about its roots. That's very simple. But we're going to understand what do these operations do to the roots. What happens when you apply derivatives? So first, I'm going to talk about keeping track of an upper bound on the roots of a multivariate polynomial. And these will always exist for real stable polynomials. I will say that a vector w is an upper bound if the polynomial has no roots that are strictly above it. So it means that this quadrant here is free of roots. So we're going to want to keep track of upper bounds on the roots of the polynomial. And eventually, we're going to set all the variables to be the same. So accordingly, I'm really going to want w to eventually be a diagonal vector. I want all of the coordinates to be the same. We're not, but we'll move around before we get to that. OK, now let's see what subtracting derivatives does. So this is an example of a particular bivariate real stable polynomial, and I just plotted its roots here. I want to give you an idea of what subtracting off the derivative does. It basically shifts the roots up, but the nature of the curves that they trace out changes a bit. But they interlace each other. There's a lot that you can say about them, but at least it shifts them up. And that you should have some intuition for, because if I subtracted off a very small portion of the derivative, that's a lot like just shifting the y coordinate a little bit. But we need, that's not exactly true, but we're going to prove something very similar to that here. OK, so I want to understand what happens to the roots. Let's first understand what happens when I subtract off derivatives in the univariate case. And this is really what I did last lecture, but I'm going to explain it in a different way. OK, so let's say I take a polynomial, and I subtract off the root, and it's a one-variable polynomial. What we're going to keep track of is not the largest root, which you would think, but a relaxation of the largest root. So if I have a bunch of numbers, lambda 1 through lambda n, think of them as the roots. We call that alpha maximum is the largest number u. So that's u is greater than all the roots. And the sum of 1 over u minus the roots is equal to alpha. Okay, to understand this, think about if alpha is equal to infinity, the infinity max actually is the maximum of the roots. If I set alpha equal to 0, this is a term that is much, goes out to infinity, really. And somewhere in between, this is sort of a more robust version of the maximum of the roots. And this is what we're going to keep track of. So you can think of it as some sort of number, sort of like an average, but it's a little more than the maximum root. And of course, I'll talk about an alpha max of a polynomial. That's just the alpha max of the roots of the polynomial. OK, the theorem, one of the theorems I gave you last lecture can be reinterpreted in the following way. I can tell you what happens to the alpha max of a polynomial when I subtract off its derivative. It goes up. When I subtract off the derivative, the roots shift forwards. And the largest root can shift actually an arbitrary amount. So by the way, I should say, I need statements that don't refer to the degree of the polynomial. So I need degree-free statements. That's why I need to do this. To get degree-free statements, I look at an alpha max. And then I can say, that the amount by which it will increase is at most 1 over 1 minus alpha. So, okay, the 1 max is sort of bad. If I had the 1 max, that can actually go arbitrarily far if you have a high degree polynomial. And I guess I should mention that if I wanted to put a number here other than 1, you would subtract off a multiple of the derivative other than 1. Those are the same 1. Okay, this I can keep track of. And this is really what I proved for you last lecture about univariate polynomials. So this enables us to control what happens to the roots. Oh, I should mention, by the way, I'll just put the theorem here and I'll remind you a bit about the proof, that this does give you sharp upper bounds on the roots of associated Laguerre polynomials if you apply it. So I mentioned last lecture, you just keep subtracting off derivatives, you get associated Laguerre polynomials. This is the easiest proof I know of what the roots are of those things, at least the asymptotics. Okay, there were 2 things we did in this proof. First, we looked at the Stieltjes transform. That is this term 1 over u minus lambda I, the sum of those, which is the derivative of the polynomial divided by the polynomial, or it's also the derivative of the log of the polynomial. And really what we're doing is when I'm defining the alpha max, I'm looking at the inverse of the Stieltjes transform. Or this is very close, for those who know it, to Voulez-Guazzard transform. It's just a shift of that. So what we're doing is when I set u to be the alpha max, I'm choosing u so that the Stieltjes transform at u is equal to alpha. And our proof of this theorem relied on 3 things. 1, just elementary algebraic manipulations, taking this formula and seeing what happens when you take derivatives. And it depended on 2 facts about this function, the Stieltjes transform, that in u it is monotone decreasing. The further u moves from roots, it goes down, and that it's convex. And I emphasize that because we're going to need to prove the same thing for the multivariate case. And that's essentially all we're going to need to do. OK, so now let me remind you of what we're doing and set you up for the multivariate case. What we're going to do is we want to bound the maximum root. And we take this determinant and we subtract off derivatives in each variable. So what I will do is I will say that a vector w is not just an upper bound on the roots of a polynomial. I'll say it's an alpha upper bound. If it's an upper bound and in every coordinate, it should be an alpha max, or better. So it should be an alpha I max for alpha I less than or equal to alpha. So this sort of means it's not too close. Not only is it above the roots, it's not too close to many of them in any given coordinate direction. And the theorem that we want is that if w is an alpha upper bound and I subtract off the derivative in, say, the jth variable, I can compensate by moving w delta steps forward in the jth variable. So I move it a little bit forward, where how much is delta? It's 1 over 1 minus alpha. It's exactly that term we had about how far the alpha max moves. Yes? Yeah. Yes, right. You fix all the others. So right, because I've got z, right, so I fix all the others to w, and I just look at varying one of them. So in each coordinate line through that point, I want it to look like an alpha max when I restrict. Yes, to that exact point, yes. So we now know, OK, so what this theorem will tell you, and I'll tell you a bit about how we prove it, is that when I subtract off each of these derivatives, I can compensate by moving my vector just a little bit in the corresponding coordinate. And I'm going to subtract off each derivative once, so I will move my upper bound once in each coordinate. I'll take a little zigzag path along the outside of the hypercube. OK, so how do we prove? Yes.
W will move at the end of the process to a point which is the 1 over 1 minus alpha.
Exactly. Yes. It'll move further by that amount. It won't start at 0, but it'll start at something diagonal. Right. OK, so the same proof, it's basically the same proof as before, but what we need to know is now we need the same fact for multivariate real stable polynomials. That if I look at the derivative in zi, I need to know it's decreasing in convex in every other coordinate. So if it might be hard to see because they're small, but this I and j are different. But all we really need to know after the algebraic manipulations is that when I look at a real stable polynomial and I divide the derivative by the polynomial that is convex and monotone decreasing in every other coordinate. And this, it turns out, there are many, many ways to prove. So my favorite way, and the way we wrote up, follows from a theorem of Helton and Vinokhov. So if I'm only looking at 2 variables, then I can restrict all the others out, and I have a real stable polynomial in 2 variables. And they give us an exact characterization of the real stable polynomials in 2 variables. They can all be expressed as a determinant of a symmetric matrix A plus a positive semidefinite times X plus a positive semidefinite times Y. So this is a huge hammer that I emphasize because I think it can be used for many other things. But once you know this, you can really prove anything about the polynomial. So once you know this, monotone and decreasing, convex are very simple. There are other proofs I should mention. So one actually was pointed out. Yes?
Are there similar characterizations? I mean, you could guess that every trivariate.
That's false. That's false, yes. The generalizations don't hold. I think the first proof I remember was actually related to matroid theory. So there's some way of looking at the non-zero coefficients you get, and they form a matroid. At least that's the paper that I remember it appeared in. But yeah, you can't do that in general. OK, so Renninger pointed out to us actually that this is also implied by a result of Bauschke, Guler, Lewis, and Sendov. So what they were doing is they were looking at a generalization of semi-definite programming, for those who know about this, but to programming in the cones of upper bounds on real stable polynomials. And they defined a barrier function that you need for interior point methods, which sort of inspired us. Actually, that's a different one than the one I study. But in their paper, they also mentioned, oh, there's this other barrier function. It's the same one we study. And these convexity properties follow from their results as well. So you could do that. And Terry Tao gives a mostly self-contained proof in his blog. OK, so that's what we do now to get started. Right, I told you, the determinant, the first polynomial you know everything about. So if I want to understand, what are the derivatives in a particular variable of the determinant, this is Cauchy's formula. And I divide it by the polynomial, I get it's the trace of the sum of the zi's times ai. And if I set all the z's to be the same, I can just say this is a epsilon over t when I set all of these to be t. And epsilon was the upper bound on the norm of the ai's. So we know we can actually get an alpha max when we start. And then it moves up in each coordinate. We get a diagonal point, and we prove a bound on the roots. OK, so this was our end result. And this is what you need for Kadison-Singer. Yes. Oh, yeah, sure. This was just the calculation we started with. So now you need to play with the parameters a little bit to optimize it, which we do. So we figure out what t do you want to start with. So you get a certain upper bound. This gets you what your alpha is and your alpha max, and figure out what's the right step. But it's really only one parameter to optimize, so it wasn't very hard. OK, so here's another interpretation of this. If you want to think probabilistically, like we were talking about earlier, one way of saying it is if I give you a bunch of vectors that are random and independent. OK, I wrote finitely supported. Oh, right, because I'm going to say probability bigger than 0. So the sum of the expectations, or the sum of the covariances is 1, and the norms in expectation are always bounded, or the squared norms in expectation are bounded, then there is some probability, non-zero, that the sum of the outer products has a norm bound like this. And this is sort of a shaving of a log factor off of what you would get for high probability results. Yeah, log in the dimension, right. And this is dimension free, right. And so this gets us our main theorem to remind you that if I have vectors all of bounded norm, then I can, and oh, I forgot that there's a sum, there's a decomposition of the identity. But OK, we need that. Then you can put them into 2 parts so that the norm of each part is very close to a half. And that implies, Weaver's conjecture KS2, and that applies Ackermann, Anderson, and that was known to imply Kadison-Singer. But it's sort of a long derivation to go from there to Kadison-Singer. So it's a much shorter trip if you start with Anderson's paving conjecture. And that differed, as I mentioned, in an important way. When you turn it into a statement about vectors, we just know the vectors have norm squares at most a half. But to compensate, you're allowed to partition into more than 2 sets. 2 sets would fail. But you're allowed to partition into many sets. And then you need to get the eigenvalues bounded away from 1. And you do this using the same technique. As opposed to picking the vector at random to go in one of 2 sets, you pick it at random to go in one of k sets. And then once you know the facts, the analysis is immediate. OK, so here are 2 conjectures. So I told you that our argument breaks at a half for two sets, but I think that's exactly where it breaks. Meaning, for any number less than a half, if all of your vectors have squared norms less than a half, then I believe you can partition them into two sets so that the norms of each set are all bounded away from 1. And the epsilon will depend on beta, and when beta is small, epsilon is going to be small too. We have a bunch of conjectures that would actually imply this. That sort of distracted us and probably took a year off from the problem because we believed something, from solving because we believed something very strong was true. We haven't proved those yet, but maybe someone else will, and then we won't lose sleep over it anymore. Another conjecture is that exactly what I told you is the extreme case asymptotically for these mixed characteristic polynomials actually is. So again, this is the analog of Gurvitz's theorem, that if I want to actually make the maximum root of the mixed characteristic polynomial as large as possible, given the conditions on the sum of the matrices and the traits, that they actually all should be multiples of the identity. I have a lot of experimental evidence for this. And again, it was such an appealing conjecture that I think we spent too much time trying to prove it instead of just getting an asymptotically right bound. Yes? No, I believe this is true for every single dimension exactly and tight. And we can prove it in a neighborhood of the identity matrices, but not a big enough neighborhood to do it in general.
So it's not even known for epsilon equals 1?
No, it's not. Right, epsilon equals 1 is exactly the case where bounds on the permanent would apply and such things. And actually, if you can prove it for epsilon equals 1, then you can do it for any epsilon. So there's a way of extending such a bound. Yeah, these things, there's a lot of nice structure between these. So let me finish with some open questions. One is, can you find this partition in polynomial time? Or is it computationally hard? I have no idea. You're not going to do it by our proof, but you could imagine doing it by another proof that might be constructive.
Local lemma found.
Exactly, right. Local lemma, right, we now know how to do efficiently. What else can one construct this way? OK, next lecture I'll be telling you about how to construct Ramanujan graphs this way. There are a few other things we can do this way. Various very tight proofs of Bourgain-Tzafriri's and Tzafriri's restricted invertibility principle. And OK, some other Ramanujan graphs that I won't talk about tomorrow, but it feels like the technique should be used for proving a lot of things. There are a lot of nice families of polynomials that are real rooted. And I think there's a lot of theory to develop here. And part of the theory that I'm trying to develop is just understanding how operations that preserve real rootedness actually change the roots. So you can find books on this topic. It's a classical topic of here's some operation on a real rooted polynomial that keeps it real rooted. But that's a qualitative statement. We want to make it quantitative. And I think it's a challenge to do that. But that's the sort of thing you need in order to be able to use these techniques to prove theorems. OK, thanks.